welcome. Welcome back. A couple of important announcements. Actually, only one. At 5:30 today at our house in the living room, we're having a heat pump hot water discussion. There'll be some people that actually like them. Then there'll be the rest of us. Okay, that little bit of, wet humor. So our living room at the house, 5:30. There'll be a serious discussion on heat pump hot water heaters. You want to say yes?
For those people that are working in humid climates, we're going to have a little breakout session this evening, 5:45 to 6:15 at the test hut, which is behind the parking lot at Joe and Betsy's house.
Yes.
Heat pump hot water heaters.
Hot and humid climates, vented attics, insulation levels, and moisture storage thereby.
In the backyard of the house, behind all of the cars, before the deer fence. Pardon me? I want that meeting to be later because we've got a heat pump hot water meeting. No?
The only time slot we could get. So we're going to have competing meetings. You got to pick one.
No. What we're going to do is I'm going to make sure you have a slot tomorrow.
Okay, that'll work.
No. No, I mean, I don't tell anybody I was in charge, okay? All right. Thank you all for coming back, and it's again a tremendous pleasure to introduce the next speaker. We actually met playing beach volleyball. Used to be quite a famous beach volleyball player. Mark is also louder? Huh. Thank you, Andrew. Well, I've never had one of my kids tell me to be louder. That's Andrew, my son. Anyway, Mark is a professor at a pretty reasonable university a wonderful university, UC Davis, and he invented Aerobarrier. Are you freaking kidding me? Wow! And so, yay! Woo! You had to do that because things sucked. Oh, okay. So without any further ado, please welcome my friend, Mark Modera.
Okay, is my mic loud enough? Can you hear me? Okay, good. I can only go so loud. At any rate, so first I should manage expectations. So talks earlier today were pretty much on like fairly broad topics. And now all of a sudden we're just going to go and go down into like one very specific topic. And that's fine, as long as everybody realizes that's what we're doing. The other thing is what we heard about is that particles are the problem in the last talk. That's what I do. My business is creating particles, so it's my fault. We also heard about electrification. Another part of my talk is going to be inverse electrification, but not for the building. But at any rate, and then, okay, let's just get started because I have to get through this. So my first thing I need to do is, since it's such a specific topic, raise your hand if you don't know what aerosol sealing is. I never thought I would see this moment. When I started this stuff, we're talking about how long things take. the idea to do aerosol sealing I had in 1987. So that's almost 40 years. So when we talk about changing standards slowly, things move way slower than you like, except when you don't want them to. So I will sort of dive in a little bit of the history. This started out with duct systems at Lawrence Berkeley Laboratory. Aerobarrier was after I sold the company once and gone back and became a professor, and I was allowed to do kind of whatever I wanted instead of being a businessman. And so I thought, well, maybe we could do buildings. So anyway, but today it's like a Whitman sampler from me of like where we're at. And some of it is nerdy, some of it not so bad. Okay, presentation overview. I'm gonna use an equation. I know with this many people, that's always risky, but I made really big font. So hopefully that'll work. Talk about how you would analyze how well something is sealing, and talk about something called transport efficiency. It's a little bit of a throwaway term, but we'll see. Then actually, what the kind of interesting thing is in academia, you're always fighting to try to get good technology to do your experiments and all that. I discovered that my job right now, I'm called Chief Scientific Advisor, which means nobody reports to me. I don't have any budget. I don't have any authority. But they all listen to me anyway, which is kind of cool. But I also get the CEO to buy me nice toys. So we got to buy a fancy particle analyzer, and we got to build a dedicated test facility for looking at Aerobarrier and figuring out how to make it better. I'll talk sort of where the technology is going. Some of it is here, some of it is not yet. And then a little bit about some new applications. Okay, so this was in case everybody, when they didn't raise their hands, didn't know what it was. So basically, you pressurize a building with a fan. It's kind of a blower door on steroids. And what I mean by that, it's able to produce higher pressures. Blower doors, people are talking about why do you have 50 pascals? It's because blower doors don't like going much higher. That's not true. But realistically, we sometimes want to make the building go to a higher pressure than that, and you have a different kind of fan, right? Instead of a axial fan. And then you spray a bunch of sealant in the building. I mean, kind of seems simple in concept. And then at the end of all this, or actually during it, you track what's going on. So this sort of taking data like that started in 1997, somewhat, actually not somewhat. I have to do a sort of a shout out to Gary Nelson and Colin, that I went and stayed at Gary's house, and he worked with me a little bit because I just had this idea to do this stuff, and was like, well, we can track it. And that has evolved into the point where the data on every building that ever gets sealed or every duct that ever gets sealed goes to a server, and we can now look at it and slice it and dice it however we want and figure out how things are going. I'm not controlling or anything. So conceptualization of the envelope sealing process. So this is no, I got two equations, sorry. So I just wanted to point out that if you want to know how fast something is going to seal, we want to know how those leaks have to go from a certain size down to 0 or close to 0. So the rate depends upon basically how fast I can dump sealant into the building. And that's determined pretty much by how humid it is, right? If you try to put too much water, sealant's water-based, try to evaporate too much water, it's going to rain, it's not going to work. Then the next thing is you have to figure out how much of the sealant that you spray in there actually makes it to the leaks. And then once it gets to the leak, how much deposits? And then how much sealant do I need to seal that leak? And so it's a pretty simple equation, right? We're good with that? The reason I put it up here is I have to do this inside the company to explain to people to look at the big picture. I also realize that the way people think about things, they tend to look at the answer at the end. Like, what, am I faster? Am I slower? And I think that's pretty much useless unless you understand why. Because if you don't understand why, you don't know what to do, what to change, how to improve and all that. So we designed this facility to be able to measure all these different parameters sort of simultaneously to see what's going on. So transport efficiency, this is a pretty simple concept. If you put a bunch of particles in the air, what do they want to do? They want to fall down. And you want to come up with a way to say, well, how much are they falling down versus going to the leaks? So if you basically say it's a race between getting to the leaks before they fall to the floor, you can actually turn it into a flux. So back to here, I think I go backwards, yeah. Settling velocity is a speed. And you take a speed, multiply it by an area, and you get a flow. So you can say the particles are falling down at the settling velocity to such and such an area. And then you just compare that with how much is going to the leaks. Well, what's going to the leaks is exactly what you're putting into the fan. Otherwise, the building blows up. So end result is you get a simple definition for this transport efficiency. And we don't have to go through this, but basically the whole point is just to be able to compare apples with apples. And how do you do that? So I get to do kind of whatever I want, and nerds tend to do nerdy things. So what I did is I developed a minute by minute or second by second, whatever, model to predict exactly what an Aerobarrier process would look like, and to adjust all the parameters, all the knobs you get to turn, and figure out when you turn that knob, what's going to happen. So I've got a model and I've got a test facility. So this show was actually built. Someone had the bright idea that we should build 2 of them. We have enough to handle just running one of them at a time. So the second building just becomes a staging area. But basically we built a building within a building, and we put in a bunch of spots to put leaks. And basically they just clamp in and out. And in addition to putting the plates so that we have the leakage and we can take them in and out and measure them and change them and clean them and all that, to measure that transport efficiency, we came up with sort of a cheapo way to do a personal particle monitor. So basically you take a vacuum pump, you put it onto a little box, and you suck the air through a filter on that box. You weigh it at the beginning and at the end, and you've got the average concentration during your job. And even came up with something that I just filed a patent on, is the idea that you could not only get the average concentration, but you can get the minute by minute concentration, instantaneous concentration from that same box. So I said, go ahead. The filter. I mean, if you have a super, super deluxe scale, I suppose you have to weigh the box, right? But it's much easier signal to noise to do the filter. So these are leaks. And so we make all the same, like there's 20 plates of leaks all through the building. And you'll notice they're made of aluminum. So we also weigh these plates. So we have a scale that's good enough. You can weigh the entire plate before, and you can weigh the entire plate after, and you can figure out exactly how much sealant was required to seal those leaks. The interesting thing that's not in the picture is we started out with, I guess it was pressboard. And there's a real problem with doing with pressboard, as most of you in this room probably know, which is you weigh the plate before and you weigh the plate after. However, when you're doing the sealing, there's all that humidity stuff that's in the air. So the plate takes on humidity. Then you have to dry the plate before. And if you keep on drying it, you got this exponential curve, not all that much fun. So we threw out all those plates and switched over to aluminum, which I know is not as representative, but is much easier to deal with. Basically, I said all this. We also weigh the sealant, so we know exactly how much sealant went into the building. We know the percent solids. I have this much mass and that much mass. There was one other point I was going to make. There was we talked about embedded carbon, and somebody asked me, his name is Mike Lubliner, said, so what's the embedded carbon of your little aerosol thing? And I decided to ignore the energy you use when we're applying it, but in the actual sealant itself, I think we use somewhere between 1/10 and 100th of the amount of mass of sealant to seal the leaks, because the sealant goes where you want it to go, as opposed to having to put in like 10 times as much as you need to close the leak. Now, there's a whole thing we could debate about that, but we're not going there right now. Anyway, in terms of materials, it's a much smaller amount of material. So technology developments. So this is kind of what the system looked like. It had 220 volt fan. This thing that says Van Air on there, I discovered that we built this. I wasn't paying attention. It is a giant compressor diesel set where you're burning a bunch of diesel to generate electricity, to warm up the air when you put it into the house, and to run all these compressed air lines. And it struck me as being incredibly dumb to burn diesel, create electricity, then go take the electricity and turn it into electric resistance heat. So a very simple improvement was, why don't we burn the diesel right in the air that we need? And so what end result is, we wound up saving 35% of the weight, a whole bunch of volume, and everything became a lot easier to deal with. So that is currently available. The next idea was, when you want to make aerosols, there's sort of two ways. If anybody does paint spraying in their house, there's an air and there's an airless. And air is easier to control in some ways, and you can control the pressure, et cetera, but you have all those tubes you have to run into the house. So the idea was, if we could switch to doing an airless system. The idea being, we don't have to run the compressors, we don't have to run the tubes, any of that stuff. And now you can fit everything, so almost in a pickup truck, right? Not much better way to do things. There are problems with doing that. Everybody here knows when you have a technology and you've been sort of working with it for 20 years and you have a new one and you start doing that, it doesn't take like 10 days to make it work, right? And so it's been a challenge for me to get people to sort of realize that it's worth the extra effort, because it makes bigger particles. There's all these things that you have to deal with. So I'm going to shift gears one more time and talk about the test facility, and I'll get back to the air versus airless. So in this picture, what I'm showing is we put 4 boxes of those boxes on the walls of the structure, and we measure the concentration. And what you see, let's see if I could, do you see my cursor? Yeah, I think so. Oh, no, you don't. No, sorry. All right. And I can't point at anything, so I'll wave my arms. There's a box at one end of the building, box at the other end of the building, and a box in the middle. So if you look all the way to the right in the picture, what you see, it says north over south. Those boxes should be giving the same answer, right? In terms, if it's symmetric, and they kind of are. And the middle, the one that says middle, is higher. You have a higher concentration there. But the other thing we discover is that if you put it high up on the wall or low on the wall, you get a different answer. Not a big surprise, but you want to quantify it. And so came up with a very easy way to quantify it and figure out, when you go from one test to another, when you turn a knob, you both figure out how well it changes the transport, how well it changes the top to bottom, all that kind of stuff. So it's kind of fun. Okay, so here's our lab. The plot, if you'll notice, looks different than the plots. You're going to see other plots for Aerobarrier, and they all go like this. And this one kind of does like that. Part of the reason is that leaks in buildings are like somewhat random in terms of their size and shape, whereas the leaks in our chamber are all exactly the same. And so how well you deposit in a leak goes with the square of the size of the leak. So of course you've got the net equation, you've got things fighting each other. And this is exactly what it should look like if all the leaks look exactly the same and the kind that we made. So this is with a compressor. And then we did airless. Well, let's just say that people don't think this is a good thing. It now takes longer to seal. However, a magic thing occurred, and we now have airless. This is in the space of a month, right? We turned a bunch of knobs. This is showing 3 tests. We did 21 different tests and figured out how to make it happen. So this is kind of cool because when people are telling you no, something won't work, or no, this is stupid, and you get to kick their butts, that's a fun, I like that stuff. The other thing we found, this was like hot off the presses from last week, was that, well, this we knew. It saves about 20 minutes on setup and cleanup without having to run all the tubes everywhere. But it had longer injection time, so it was not really winning. But last week, it showed shorter injection times and still got the 20-minute savings, so Mark wins. Okay, so I'm going to shift gears. I've only got a couple more slides, and then I'll leave everybody alone. Ceiling plenums, which this room is actually not a good example. Most of the time, most places you go have a ceiling plenum return, and right here we do not. But everybody here knows, and raise your hand if you know what a ceiling plenum return is. No, if you don't know. Okay. It's a negative. I go with negative questions all the time. So basically, one of the things I discovered was that those things, they can leak to outside. And in fact, right, it's a negative pressure. It could suck in outside air. So we tried to figure out if we could seal it. And the nice part, you're going to hear more about existing buildings, about attic sealing. But a ceiling plenum, you can basically think of it as I can put my injectors up there, and then I can pressurize the room, and the air goes up into the ceiling plenum and blows the particles out of the building. Now, this picture at the bottom, that's unfortunately what the top of a building looks like, with those nice, the corrugated roofs and those big gaps. And you can seal those somewhat, but they're not trivial to do. Anyway, long story short, blah, blah, blah. We put in some stations, we ran the thing, and so this shows that we actually did it instead of just drew pictures. And the results were, we sealed about 300 CFM50. Not a lot, it's not a big space, right? So we sealed some, but we stopped it because there was some fogging of the occupied space. So the thing we learned was that you shouldn't be doing while everybody's at their desk, right? We should have known that, but someone decided they would try anyway. I wasn't there. But what we did figure out is it's not enough fogging to cause any deposition that anybody would care about in those rooms, but it was enough fogging to have people be like, what's going on here? And remember, particles are the enemy. So that was like I'll call that mixed results. And then one more application was to do an underfloor application. Basically, like in a computer room in a data center, they tend to do a raised floor and put all the stuff under the floor. And this turned out to be a piece of cake. We basically even just used a duct sealing machine to pressurize underneath there. And so the results were, we sealed in, I don't see how much time it was on here. Well, sealed 90% of the leakage and reduced not only was it leakage to the room, but it was leakage to the outside. We did a blower door test before and after of the room. Okay, So I promised to quit and I will. So the takeaways from what I feel like I brought across today is that I think we came up with a really nice facility. And if you have any bright ideas that you'd like to see somebody try out, if anybody here is actually using it, we can test it. Unfortunately, we're in a happy spot now of having more ideas of how to make it better than we have time to do it. So now we have to prioritize things, it's a really good problem to have. What's cool is it separates out the factors influencing performance. I'm going to declare victory that airless envelope sealing is the future, well, relative to air-based envelope sealing. It's not the future of everything. And then I talked about new applications, and I finished with like 2 minutes to spare. So I can take questions now. Okay, you go first.
Here over installation of in the pump, fire safety, life safety point of view.
Meaning like we do all the fire smoke rating stuff on it, like compared to other caulking stuff like that. It does fine with that. People have approached us can you make this be a substitute for like this red looking stuff they call fire stop? What's that? Okay, and honestly, it hasn't. I'm not the chemist, but I think we could figure out a way to do that. So we're not there now, but in other words, the short answer to your question is, it's not a fire hazard, but it's not like a.
Is it possible for you low enough to be installed on a certain pump?
0 and 0.
Okay.
Oh, this guy was next.
No.
Oh, sorry.
Go in.
Oh, wait, he's in charge, not me.
Hi. So can you talk a little bit more about the test facility and what your main purpose was?
The only purpose of
Okay.
it is that I get to play. Right.
Great.
So I get to play with, like, can we do it? It's really hard. So you look at field data. We actually get, I don't know, lots of data every week, and we change things in the field. And so we look at, if we change this, what happens? But if you do it in the lab, we made a lab just for this purpose, right? We're looking at all the different knobs you can turn.
Right. So it seems like the main purpose for the knobs that you're turning is to reduce installation time.
Correct.
That's your #1 goal.
Oh, well, there can be other goals, right?
Okay.
Reduce what gets deposited on the floor. It could be, we want to try a different sealant material. What happens if we start using a different sealant material? Is it going to affect things?
What about temperature, like ambient temperature? Like
Yes.
these
Yes,
for buildings
yes.
within a
So
building,
we can
right?
change the temperature. We can change how much heat we add. We can see what happens when it's a rainy day, right? What do you have to do? So that model that I showed, the one slide, I was going to go through and do it, but I couldn't make it work well. But basically, I figured out that if it's 90% humidity outside, this is a really profound discovery. If it's 90% humidity outside, bringing more air does not help. All you have to do, your only choice then is to add more heat. And surprise, it works.
Thanks.
Sure.
My question was about with the new sprayers. Was it much more about the diameter size of the particles versus the sprayer itself?
Okay. You want to go to the new sprayer because of all the advantages of not having to carry around a bunch of extra stuff. But the downside is, in general, an air-based system creates smaller particles than a non-air-based system. So the airless system, we went through a lot of work with nozzles and with changes to this, that, and the other thing to make it that we can get, it was called a 3-micron nut, right? We wanted to get 3 microns smaller, and we basically got there and even did better.
I have a question about the product itself. So it's an acrylic sealant, right?
It's, let me think. The current sealant, is it acrylic? One was poly, yeah, I think it's an acrylic now, yes.
Have you done any testing to see how it performs long-term? Like, I know obviously it's dramatic improvements in air sealing when it's first applied, but what about a year, 2 years, 10 years later?
Okay, that's always a $50,000 question, or the $64,000 question with inflation. So basically, I've had that bugaboo. I started dealing with that question in 1993, right? At which point, no, it was later than that, 1995, right? And so the problem is when you try to do accelerated testing, it's really difficult. So I built a little test rig. We let pressure go up and down, blah, 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 blah. The test rig started breaking and the seals were fine after 4 years of accelerated testing. So there's models that you can use. We even built little things that you make a seal you make a plate, you have like this, and it's bolted together, and then you take the bolts off and you go like this. So we've done all that kind of stuff, and we really haven't gotten to got it to fail, right? So every sealant, we spend time doing quotes accelerated testing, but it's hard, right? We may at some point just do a study of going back to some buildings, but that's really hard too, because people change things, right? And other parts of the building, like the windows, we don't seal the windows. The windows get leakier. It's hard to go back and do a check, but we're doing sort of both. There's a whole bunch of things for testing plastics, right, as to their longevity, and you heat them up to a certain temperature and you do all that stuff. We're doing all that stuff and we haven't seen anything that suggests we got the wrong horse. That's a long-winded answer. I wish I could give you the answer is 3, but.
Nice, thank you.
No, the answer is 30. I'd rather that one.
Thank you.
So I've seen the report on the testing over long-term and rapid aging. And when you do this, you do it open cavity. So it's mainly sealing out at the sheathing, the wood and pipes that are going through. And that's completely different than on a plate that's all metal going between or all wood. And so I've actually proposed some testing to Aerobarrier in terms of sheathing to wood joints, copper pipe to OSB sheathing. And then if you do it after the drywall's up, now the seal is largely between like a plastic electrical box.
Plastic box and sheetrock. Those have
And
pictures of
gypsum
that.
board is a bond break for exactly that type of sealant. So I think a lot of the answers about how long this lasts is going to be related to what are the materials it's sticking to and how differently do they respond to both temperature and relative humidity changes. Because like the wood's going to be not going to care about the temperature, it's going to care about moisture content. Plastic pipes and metal, it's not going to care about the moisture content as much as it is contraction and expansion with temperature. So.
Well, we did the temperature thing, but we didn't do the dissimilar materials. And
Yeah.
I'm always, all right, since I don't have to do it and I could just say, make it so, I'm always in favor of if someone has ideas how to make it better, that people will be less nervous about it. I'm
Well,
all in favor
we
of
actually
that.
wrote up a test plan and I'm going to share it.
Oh, please do.
My question is, what's the upper limit for the size of the hole? And is there any shape limit for the size and shape of the hole?
Okay, so let's say, I've heard that question once or twice before too. Yeah. So in terms of the shape of the hole, it's not that big of a deal. That's not an issue. The issue is sort of the minimum dimension of the hole. In a duct, if you've got a velocity in a duct where it's going like this and you have a slot like that versus a slot like this, it makes a difference. But in a building, you know, like the long skinny slots, that does not seem to be an issue. Diameter, so I'm getting there. So the answer I gave for maybe a few decades has been that the efficiency of sealing a hole, that it was actually that deposition efficiency in my equation, it goes with the square of the size of the minimum dimension of the hole. So what I would say is, if you have an 1/8 inch gap versus a 1 inch gap, the 1 inch gap takes 64 times longer than an 1/8 inch gap, which at some point becomes like impractical to do it. So in terms of a maximum size hole, we have sealed 1 inch gaps. I would not recommend it, right? So the numbers you've probably seen on websites and people making claims and all that are anywhere between 1/4 and 5/8, right? But the right answer is kind of what I said, right? Which is that, yeah, you can seal big leaks. I mean, you can't seal holes like this, right? but you can seal a hole like that. And but in general, you don't want well, practical limit, we give a practical limit of like anywhere between 3/8 and 5/8 of an inch as being practical.
So,
A long-winded answer, I
so
know.
Mark, my question, I think, is a simplistic version of what Peter was getting at, which is the dissimilar materials that you select for, the slotted aluminum sheets or plates or whatever you call them.
1 second. Somebody in potential spam is calling me.
So,
And it's ringing in my hearing aids. You couldn't tell, but
so when
sorry.
I saw the photo of the aluminum slotted things, I thought, well, boy, I think I need you to explain how you could rationalize that that the stuff that's gonna stick to aluminum in a similar way that it's gonna stick to wood, which has all kinds of.
No, actually, that part is easy. That works. That's not an
Could you
issue.
explain it to me? Because I don't understand.
It's difficult. Basically, if you have something that has a high adhesive value, so there's adhesion and cohesion, right? So once you get the adhesion, once you get a sort of a monolayer on the surface.
Right, it's that first layer that I was.
Yeah, exactly. So what we discovered is that different materials, it doesn't change it very much, because we did it with wood, we did it with sheetrock, we did it with metal. So the point of the metal is we're not really testing, that test is not meant to
You
test
tested
the
something else, yeah.
adhesion. That is, and since it works, basically we're seeing the same rates of sealing and the same profile of sealing with wood and with metal. We can use the metal because the metal's way easier to clean.
Right.
And doesn't absorb moisture.
Have you done any evaluation of like amount of sealant that escapes during seals and?
Yeah, we have
quantify that
exact numbers for
environmental?
that.
You have exact numbers or you don't?
We do.
Oh, awesome. That'd be
Right,
great.
so it depends, this depends a lot on the size of the leak, right? When you have little leaks, so I'll do ducts for a second. In ducts, if you have slip joints like this, none of it gets out, pretty much, like very little, like 20% of what makes it there. So on average, you're getting, let's say, to the leak itself, somewhere between 40 and 70% of the leak of the sealant makes it there. In Aerobarrier, it's falling out on the floor. In a duct, it's falling out in the bottom of the duct. Then, once it gets to the leak, you've got deposition efficiencies, which is what you're talking about, of something like, I would say, 30 to 70% again. So you have to multiply those two numbers, and what's left is what's going out through the leak, right? Does that
Yeah,
Does that answer
exactly.
your question?
Yeah, and the question comes up for us, for clients concerned about like overspray and microplastics in the environment and things like that. They're wondering how much is getting out. My sense is it's not that much, but if you're starting with a leaky existing building, likely holes that are larger, there might be a lot escaping at first, and then you kind of reduce it. So just
Yeah,
curious.
that's
about it.
over the course of the process, it'll go from
Yeah.
more escaping to less escaping. But the thing to remember when I made my smart-ass comment about the embedded carbon is that the amount of material that you're using is very small, right? Compared to. Okay, 1 second. You're gonna make me do math. We use probably, I wish I had the top of my head. Let's say 2 gallons of sealant for a building. I'll make it 5 gallons. I don't think it's 5 gallons. I think it's more like 2 or 3. But if it were 5 gallons and it's 20% solids, that'd be 1 gallon of solid material for a pretty big house.
So Mark,
Wait, you're not allowed to ask
I
questions.
know, I'll be up in a little bit, but this is pertinent to this conversation. So at the Home Performance Building Conference, I found out that Earth Advantage has already started retesting houses. So they've sealed a bunch of new homes. This is out the Seattle area, Portland area, I think.
Okay,
sealed a bunch of new homes and now they're going back. I think it's a couple of years later and they're retesting. They're doing air leakage tests on those. So small sample, early results are very small changes in leakage. More to come.
Thank you. One comment on that, by the way, you know, all those silly corrections in blower door tests and stuff like that, like for pressure and for humidity and altitude and all that. I discovered, not big discovery, but you do a little bit of math. And when we're sealing at one temperature. And in the winter, you have to pay attention that the air is coming into the fan at one temperature and leaving at another temperature. And then when someone comes back to do a test for a HERS rating, they're at yet another temperature. And if you don't do those corrections, you can have differences other than the differences like in the prep, right? When you unprep it, there's a bunch of leaks you open back up again. So with the kind of changes that you're going to see, you have to be very careful how you do the measurements. Yeah.
So two-part. Are you still selling these or are y'all taking them all in-house now?
I don't know. I don't think so. I don't know, but I should know, but no, I shouldn't know, right? I'm chief scientific advisor, no business, right? And so basically, I know we were selling them. I think we're still selling them. I know we do in-house also. So I'm not sure.
Yeah, recently I was trying to purchase one and they were saying they're going
they
turnkey
told you
only.
go away?
They said you're doing turnkey only.
Really?
Keeping it in-house, yeah.
But this is great. I get to come here and to learn about my
So,
company.
But the second part was we're trying to do it on a remodel. In that remodel, we weren't removing flooring, cabinets, countertops, none of that. We're just trying to better air seal this. We had results, just the amount of taping and prep you got to do to get it to not go where you don't want it to go.
I understand.
I mean, is
So-
there a better method to that now?
All right, so this is a setup for the next speaker because what he's been doing with the same fellow I worked with at UC Davis is they, instead of putting the fog inside the house, you put the fog in the attic and you suck on the house and you suck it in from the outside and then all that prep goes away. Although we have actually done sealing jobs like in a school where you just took all the desks and stuff and pushed them in the middle of the room and you draped over them, and that worked. But in general, if you go to a house with a bunch of knickknacks and a whole bunch of horizontal surfaces, I think suicide is an option.
Yeah, exactly.
Thank you. I think the gentleman stole my thunder a little bit. I just had a very practical question. So what he just reinforces is that this stuff is sticky, right? So when you blow it, and when you blow it in the house, it goes everywhere. And the falling rate means something's going to go on the floor, et cetera. When I'm on the job site and I'm an architect, I'm walking around. Am I seeing things on the floor? Am I seeing, how do I know it all got to where it's supposed to go? And what happens to the ones that didn't go where it's supposed to go?
Okay, so 99.9% of the jobs are done in new construction at rough-in. And so nobody cares, right? But the big difference, one big discovery is when we went to Aerobarrier from AeroSeal, from duct sealing, was we now have sealants that don't have a bunch of residual tack. So that if you look at the tack for the duct sealant, it's like tacky forever, like some people. And then there's residual tack. As they get older, they get less tacky. And that's the sealant we're using now. And it makes a pretty big difference.
Just to follow up on that, because I will say most of what we're doing is renovations of often quite old buildings where you just can't get to there's plaster on top of masonry and all those kind of things. So in fact, we will usually be walking into something that has some finishes and stuff in it. So anyway, okay, thank you.
So in that case, if it's an existing building, if there's an attic, I mean, you're going to hear about it. I'm stealing all their thunder. I'm also using up more their time. Sorry.
Got a plan for, the handsome guy here, you're going to be speaking.
So I would just ask anyone that's working with an Aerobarrier sub or who is one to make sure that the person who's doing it tests the building once they take the masking off, because all the reports I get from subs doing Aerobarrier is how much reduction they got. And then I have no idea what the CFM 50 of the building is. Actually, I only know what the CFM 50 of the unmasked portion of the building. So make them unmask the building and keep the fan in place and take a number.
That's not that hard to do. I think that's very reasonable.
Yes, thank you.